Okay, so good afternoon, everybody. Today it's a great pleasure to have Adam Pound from Southampton, who will tell us about modeling asymmetric binaries in spiral, merger, and ringdown in gravitational self-force theory. So please, Adam, take it away.
Okay, thanks for joining me, and thanks to Shahar for inviting me to give this talk. Yeah, so I'm going to be talking about kind of new methods, relatively new methods of modeling compact binaries for gravitational wave astronomy, covering the inspiral, merger, and final ringdown using this method called self-force theory, which most of you probably have heard a little bit about. Okay, so like I was saying just before this talk, I probably will not get through all this material. I was being quite optimistic about how much I could cover. But I'll start with just a broad overview of kind of the landscape of black hole binaries and why we want to use this method of self-force theory. I'll then talk about kind of the state of the art in modeling the inspiral stage, and then quite recent work on modeling the final merger and ringdown. And I'll explain why that's of interest as we go. Okay, so the kinds of systems we are interested in look like this. We've all hopefully seen images like this. Two black holes orbiting around each other. As they orbit around, they twist up space-time and send out these gravitational waves, which we then detect. Currently, we only have ground-based detectors. So LIGO, the two LIGO detectors, Virgo and Cagra. And the real workhorses here are the two LIGO detectors. So since we first detected a waveform in 2015, we've now seen hundreds of black hole binaries. Signals always typically look like this. This was an early detection, maybe 2017, where the theoretical model, the waveform template is in black, and uh, the actual data stream from the two LIGO detectors are the blue and orange. So with these detections, we've been able to do a lot. So uh, we know a lot more about the population of black hole binaries across the universe. We know there's a lot more heavy black holes than we might have thought before. So we've seen black holes of over 100 solar masses, and it was probably fairly recently that people were skeptical of whether such black holes even existed, except for very massive black holes that I'll get back to in a second. Uh, we've also, performed the first very precise tests of strong field gravity. These have been really the first detections of black hole binaries. So we've learned a whole lot. And all of this has really relied on accurate theoretical waveform models, and that'll be the focus of this talk, and really how models need to change as we progress forward with gravitational wave astronomy. So this is what waveform modeling looks like for the kinds of signals we currently detect. These are the kinds of models that are used in LIGO data analysis. So we have three phases of evolution. We have the inspiral as the two black holes get closer and closer together, emitting energy through gravitational waves. Finally, they merge into a single black hole, and then that remnant black hole rings down into a stationary state, which we think is always going to be a Kerr black hole. And it rings down with a very characteristic frequency and damping time. So we have these three different uh, regimes of the problem. This is for a kind of quasi-circular type system. In the early stage, during the early inspiral, when the two bodies are far apart, we can use post-Newtonian theory, which is a weak field approximation. At late times, in principle, you can use black hole perturbation theory because you're left with just a one black hole with small deformations, and those deformations are being dissipated away until you're left with a stationary final state. And then the traditional story over the past 20 years has been that you really need fully nonlinear numerical relativity to model this merger phase in the middle between the inspiral and the ring down. Now, in practice, we really want numerical relativity simulations that are as long as possible because we want as accurate as possible a waveform throughout the entire system. But it's really been thought to be critical to have numerical relativity for the merger phase. And then the way current models work is, well, because you need numerical relativity to get the full waveform, um, it's going to be very, very slow. One numerical relativity simulation can take a day to multiple months. But for data analysis, we need very fast models. And so the kinds of fast models we have, effective one-body theory, phenom, and NR surrogates, which are just kind of trying to basically fit or spline numerical relativity waveforms. These things combine these three pieces of information to get fast waveform models. They can be generate waveforms quickly enough for data analysis. So that is working quite well, although some of the systems we are seeing are already really pushing the boundaries of our accuracy of our models. So some of our um, parameter estimation has really been contaminated by systematics in our models that we don't control. But most systems we see this modeling approach, this modeling paradigm really works quite well. Um, but it's going to pretty spectacularly fail in the future, at least for some kinds of systems. So in 2035, LISA, the Laser Interferometer Space Antenna, will launch. Uh, it now has a definite launch date. Um, I don't remember what it is, but July 2035. I think like the 25th of July or around there. So this is a big mission, and the scientific payoff, why this mission is seen as so valuable and worth these billions of dollars, is that if you have a detector out in space, so this detector, this image is not to scale, but the basic physics is right. This detector is going to be trailing behind Earth with million-kilometer arms with these lasers. And the whole point of having things out in space is that there's no gravitational noise in space, whereas on Earth, you just have gravitational gradients creating noise in your detector all the time. And because of that, it limits how low frequency we can detect. So there's a real hard noise floor or low frequency floor on what we can detect. But once you have something out in outer space, you can detect much lower frequencies because you don't have those gravitational gradients. And detecting lower frequencies corresponds to detecting much larger sources. So there's inverse relationship between the frequency of the wave and the size of the source that generated it.
Adam, question. So when you
Yep.
say gradients, what kind of what creates these gradients?
Just everything. Things moving around in the earth. There's always just constant sources of noise,
Okay.
just shifting pieces of rock, everything.
Trucks and traffic.
That also causes
Okay.
problems. Yeah, that does cause problems. If it's really nearby, those kinds of things will cause like real sudden big problems. But yeah, there's a lot of noise that's hard to escape if you're on Earth. For
Weather,
example,
weather,
weather for sure. Yeah.
electricity,
So yeah,
anything.
electricity is a nice one because there you see exactly the frequency of the local electrical system, whatever it is, 60 hertz or whatever. You see exactly multiples of that in your signal.
But when you need to clean that up, the question is to what accuracy?
Yeah, yeah, yeah. And so that at least we know the frequencies so we can clean it, but the low frequency floor is just a mess of everything and we can't remove it.
Okay.
May I use this opportunity that we have a sort of a little break to ask you a question about
Yeah.
your previous comment? See, the way I understand the reason why the models work, and you don't really need the numerical relativity except for calibrating, is that if you expand in final modes of the final object, typically the level of excitation of the merger compared to the final state is quite small. And that's why you can do a perturbation theory in the final state. And that's why the models work. But you had some kind of a different way of thinking about that.
So that's specific to the ring down. And in fact, that doesn't really work very well. So the original EOB models, they were using just actual ring down frequencies. Um, corresponding to, the actual black hole system with the final state, that doesn't get them enough accuracy. So they use a phenomenological, just damped sinusoidal fit calibrated to NR. So to reach the kinds of accuracies we need now, you really need to push things. And it is true at sufficiently late times, linear things, linear perturbations of the final states dominate, but you have to get to those sufficiently late times. And even that is a little bit complicated by nonlinearities I'll get to later in the talk. But the real thing is the intermediate stage, the merger stage, where current models are entirely relying on NR calibration.
What I was saying is that I don't understand why, and from my understanding, I didn't get that impression, is that at least in known mergers, the level of excitation of in the merger of the final black hole is a few percent. So you would expect that perturbation theory based on the spectrum of the final black hole would work very well.
So it does work pretty well at sufficiently late times, yeah. But
Rami, the ring down cannot describe the merger phase. In the merger phase, you have two black holes that are close to each other, and this
Barak,
looks nothing like a single black hole which is
I
excited.
know, I know that, but if this
I
is
know that you
new,
know, but I'm
this is
reminding you.
no, so
So
this
you
is
need to have something else
no,
for the
Barak.
merger phase.
The no, the what I'm saying is that if you are trying to describe the merger in terms of the two black holes, it's clearly a very nonlinear system. But if you are, I mean, if only a few percent of gravitational waves are going out, and you know from numerical relativity that a few percent are exciting the black hole, then you can do a final state analysis. Now, the EOB works in this spirit. What I don't understand is why is it, if the level of excitation is so small, why is it that perturbation theory doesn't work well enough?
so perturbation theory does work well at sufficiently late times. It's the merger phase in the middle that it doesn't work well for. But also the whole premise of this talk I'm giving is that we can make it work. So let me just carry
Oh,
on.
okay, maybe I'll explain.
Okay, so the most interesting things we are going to see with Lisa, just going back there, with Lisa we see much larger things, or we will be able to see much larger things. And so the most interesting things we'll be able to see is massive black holes in galactic cores and galactic nuclei, which could be 10 to the 4 up to 10 to the 7 solar masses. So comparable to the massive black hole at the center of our galaxy, which is Sagittarius A star. And I really love this movie, which is a time-lapse movie of the center of our galaxy, showing the kinds of things happening there. So let me just open up the movie. So this is showing the motion of stars around Sagittarius A star. So I love showing this movie because for my first 10, 15 years in the field, I actually never saw anything like this. So I didn't really have a clear grasp of the kinds of things we were looking at. And so you can see there's a lot of stuff going on. And this is the kind of thing we want to capture with Lisa, except zooming in on a much smaller scale. So here, the closest approach of any of these stars is about 100 Schwarzschild radii compared to the radius of Sagittarius A star, the black hole in the middle. Whereas, whoops, let's back up. Here we go. There we go. Whereas with Lisa, we're going to see much closer in on the massive black hole. One thing we'll see is massive black hole mergers, so the merger of two massive black holes, which is kind of the most violent and loudest signal in the universe. But another thing we'll see is these extreme mass ratio inspirals. And there we will really be zooming in right in on the region right around the massive black hole in the galactic core. We'd be very lucky to get a signal like this from our own galactic center, but there's other galactic centers all over the place, and that's where we expect to see these things happening. So I said that the closest approach of visible stars we can see around Sagittarius A star is around 100 Schwarzschild radii. With these kinds of systems, EMRIs, the entire detectable signal will be within probably 10 Schwarzschild radii, or even tighter. It's louder, closer. And in that tiny region, very close to the big black hole, the object orbiting around, which will be probably a smaller black hole, but it could also be a neutron star, that'll execute, say, 100,000 very tight, intricate orbits right around the massive black hole. And because of that, the smaller stellar mass object that's zipping around, it maps out a very precise picture of the space-time right around the big black hole and other properties of galactic cores. So it's acting as a very, very, very precise probe. And because of that,
A quick question, Adam. So
yeah.
this compact object
Mhm.
for a sufficiently large supermassive black hole, could it be just a normal star?
Yeah, if you're able to
Like
see it
without
before,
getting disrupted?
yeah, if you're able to see it before it gets tidally disrupted, then yes, it can. So there have been some studies of whether it would be possible to see a main sequence star falling into our galactic core in Sagittarius A star. And that would be an incredible signal to detect because at late times it would be tidally disrupted, and then we'd have electromagnetic signal as well as gravitational signal. That would be incredibly lucky. But yeah, as long as you see it early on, then it won't be tidally disrupted. Um, but it might be too low frequency and too quiet to see with LISA. That's why we would need it to be quite close, like our own galaxy or nearby galaxies.
And then also the mass transfer may push it away from the supermassive black hole and then making it less and less bright.
Yeah, so yeah, one reason we expect to see mostly black holes is the word is I don't remember, but basically heavier objects migrate deeper into the galactic core through interactions with all the neighboring objects. And so yeah, we expect heavier things to dominate.
Mhm. Okay, thanks.
Okay, so because we have this precise probe in the form of that smaller object, we hope to get a lot out of emeries when we detect them. We don't know how many we will detect, obviously, but the kind of most common estimates are in the low hundreds, maybe a couple hundred. And if they're sufficiently loud, then we can really mine them for a lot of information. So, for example, they're just a direct probe of the massive black hole that they're orbiting around. For comparison with current with current experiments, we can get maybe 1 digit at most accuracy in the measurement of the spin of the massive black hole. But with emeries, we expect to be able to measure the mass with 5 or 6 digits, the spin with 5 or 6 digits, and the higher multipole structure of the black hole, so quadrupole moment. So we get very, very just precise picture of the shape of the black hole and whether it is a Kerr black hole as we expect or something else strange. We can also look for the presence or absence of a horizon. So these leave characteristic signatures in the waveform. So this would be, if this would be an exotic compact object, like a horizonless object.
Can you explain that? Because you said that you could probe 10 RS or 10 Schwarzschild radii away from the black hole. So how would you be able to probe the presence or absence of a horizon?
So the system gets way deeper than 10 Schwarzschild radii. That's when it kind of enters the band typically, enters the LISA band typically. We keep seeing it much deeper in, but that is not how we would look for the presence or absence of a horizon, unless it's something like a boson star. So for a boson star, we would just see the signal continue all the way in, even once the secondary object, passes inside the star. For other cases, it wouldn't be so dramatic as that, but you would be able to see the impact on the waveform through the phasing. Because if you don't have a true horizon, then you don't have pure absorptive boundary conditions at that surface. You have some amount of reflection, and any little amount of reflection will then impact the secular accumulation of phase of the waveform, and we can detect it that way. We can also look for deformability. So Kerr black holes in general relativity have zero tidal love number, so you can't deform them in the same way that you can deform material objects. But if it's an exotic object, then it will have some deformability, and the orbiting body can induce new multipole structure onto it. Now, more recently, kind of the focus on fundamental physics with MRIs has shifted quite a lot to a very effective field theory inspired approach, where the idea is for the big black hole, if you have a local EFT extension of GR, anything that you're adding to GR is being suppressed by powers of the curvature, and the big black hole has very low curvature compared to the small black hole. So if you're looking at these local field theories that extend GR, then you're probably not looking for changes in the big black hole. You're looking for changes in the small object. And so there's been a big push by Andrea Maselli and Thomas Soteriou and their collaborators to focus on classes of theories that extend past GR and really focus in on the effect on the smaller object, which does dominate in that regime. And then we can kind of test large classes of theories by looking at changes in the dynamics of the small object. Now, this is all fundamental physics things, but we'll also have very precise probes of just the environment in galactic nuclei. So, for example, MRI signals can be sensitive to the population of nearby bodies if they induce a tidal resonance. MRI signals, if you're in an active galactic nucleus, MRI signals can also be sensitive to properties of the accretion disk. And if there's a spike of dark matter around the massive black hole, then MRIs can also be probes of the property of that dark matter. Okay, so things, magical things we can do with MRIs. There's papers on that every few days. But what I want to focus on is how interest in MRIs has really shifted what we can do with waveform modeling. So this is a picture of the two main axes in the binary parameter space. So the compactness, basically the separation, how far apart the two objects are from each other, and the mass ratio. Of course, there's a lot of parameters for a black hole binary, but these are the two most important ones for modeling purposes. And over here on the left, when the two objects are roughly the same size as each other, you have the picture I showed on the first slide. You have post-Newtonian theory in the early stage when the two objects are far apart. As they dissipate energy and get closer and closer, they move down on this diagram, and then you switch over to numerical relativity. And then finally, you're left with one black hole, and you're using black hole perturbation theory. Now, MRIs, the prospect of seeing MRIs, has motivated people over really the past 30 years to go over to this side of the diagram at these high mass ratios where one object is much bigger than the other. And there you use this method called self-force theory, gravitational self-force theory, which I'll explain later on. And one thing I'll emphasize is that this covers not just the inspiral phase, but also it goes in directly into the final merger. But also we find that if you push it hard enough, it can get to reasonably comparable mass ratios. It is not restricted to the Emery regime. It maintains pretty good accuracy, much closer to equal mass. So I'll highlight that as we go. Okay, now what is this method, self-force theory? Well, we have one little object orbiting around another one, and we have a small parameter for the system, which is the small mass ratio, the small mass over the big mass. I'll also introduce 1 over that quantity, so the large mass ratio Q, which is big mass over small mass. And my figures will use different notation, which is the big mass is M1, referring to the primary mass, and the small mass is M2, referring to the secondary mass. Sorry, back up. Okay, so when we have this small parameter, the mass ratio, we can do perturbation theory. And here what we're doing is we are expanding in powers of our small mass ratio. So we're taking our exact space-time metric, we're expanding around a metric of an isolated big Kerr black hole, and we have corrections proportional to the small mass ratio, the square of it, and so on to higher order. And the reason this is called self-force theory is the idea is once you're accounting for the gravitation of the small object, a small object no longer moves on a geodesic of the background geometry. These little deformations of the space-time affect the motion of the small object, and we say they exert a self-force back on the object. So it deviates away from geodesic motion. So if you write down the covariant acceleration in the Kerr background metric, it would be 0 for a test mass, but instead we have corrections coming from H1, corrections coming from H2. And this is also where you see finite size effects. So the spin of the small object, quadrupole moment of the small object, etc., they all come in here. Okay, now why is this a good approach? Well, obviously, it's specifically tailored to the regime that we're interested in when we're looking at Emery's, this small mass ratio regime. And more recently, an important aspect of it is that the way we formulate it is that it's not just accurate in that regime, it's accurate specifically on long timescales. So because the mass ratio is very small, the inspiral is very long, it's very slow, because it's dissipating energy at a very slow rate. So we need a very long time scale, and we need to make sure we have uniform accuracy on the full inspiral time scale, this long time scale. And that's really where, or one of the reasons why numerical relativity basically can never model Emery's, because of the long time scale. You need to model a lot of cycles, say 10 to the 5 cycles, and because of this disparity in length scales, you need a lot of short time steps in each cycle. So for a current NR simulation that would take, say, a day, like the best of the best can take like a day for equal mass binaries. If you ran that same code for an Emery with mass ratio of 10 to the 5, you'd be looking at 1 billion days or 1 trillion days, probably about 1 billion. And that's just for one waveform. So that's the main reason why we really need self-force, to not just capture the behavior in the small mass ratio, but to maintain accuracy on these long timescales. Now, another advantage is that the way we formulate it these days, it's very, very fast. So unlike numerical relativity, where you need to generate a whole set of simulations and then calibrate your fast model, in self-force, the basic theory already provides a fast model. So we can generate waveforms quite rapidly, hopefully rapidly enough for LISA data analysis. So tens of milliseconds for a LISA length, multi-year signal. Another advantage of the way we formulate things is that it's quite modular. So we never need to redo calculations like you would for NR, where if you change the parameters, or if you change the theory, you've got to rerun a whole new simulation. The way we set things up in self-force, it's very modular, where we can pre-compute things and then add other things, pre-compute those, and we can, in particular, then add effects from an environment or from modifications to GR in a very modular way. It's also just kind of physically simple and intuitive, where the waveform you get out is just directly determined by the orbit of the small companion going around, which is kind of the same picture that motivated EOB back in the day, that you have a waveform that's really just tracking the motion of one body around another body. Although I should say that our waveform is sensitive to the motion of the big body as well, but in a subtler way. Okay, so how do we use this to model the inspiral? Everything we do for the inspiral is really motivated from the structure of the 0th order problem. So at 0th order in the small mass ratio, we just have a test particle, a test mass, moving on a geodesic of a Kerr background spacetime. Now, this 0th order motion is already very, very complicated, like I already showed you. But this complicated structure is really masking a hidden simplicity, because the motion is integrable. We have a set of constants of motion, so the mass and spin of the primary black hole, but then the orbital constants, energy, angular momentum around the axis of the big black hole, and something called the Carter constant, which is related to how inclined this orbit can be. So because we have a full set of constants of motion, we say the motion is integrable, and because of that, we have these nice variables called action angle variables. But if you don't know what action angle variables are, it doesn't matter. The key thing is that the motion is triperiodic with 3 definite frequencies of motion. So for this system, if it's an eccentric system, it's moving between a minimum and maximum radius like this. So that's one phase of motion. If it's inclined, the whole plane of motion is also precessing up and down. So that's one phase of motion. And then, of course, the secondary is also just orbiting around the axis of the big black hole. And so that's a third phase. So this is the radial, polar, and azimuthal phase. And we can design these variables that run from 0 to 2 pi along each of those phases and have constant frequencies. So we say it's triperiodic, 3 frequencies. And then the geodesic equation, which potentially can look complicated in Kerr, boils down to completely trivial equations. You have some constants, 0 rate of change, and then you have some phases with constant rate of change that are determined by those constants. So everything we do beyond 0th order is based off of this. And it's using this method we call a multi-scale expansion, which is very similar to multi-scale expansions that are used all over the place in lots of different kinds of orbital dynamics, but also even in things like fluid flow. Multi-scale expansions are quite common. So in this particular case, this is the structure. And the whole idea is to, once you turn on the perturbation, you account for the self force and you account for the dissipation, you account for all these things. You choose variables that maintain as much of that nice structure of the 0th order problem as possible. So you can choose some new phases that are very close to the old phases that still have a frequency that's still actually exactly the frequency of a geodesic in the background, in the Kerr background, but it's now a function of evolving parameters. So you choose some nice parameters, some nice energy, angular momentum, Carter constant, in such a way that, while the rate of change is small, so order epsilon rate of change, so these are slowly evolving, but also you choose them so that there are no phases on the right-hand side, so there's no oscillations. Everything is just slow. So a slowly evolving frequency and slowly evolving, actually forcing terms that are driving your evolution.
Can you give an example of the magnitude of epsilon in a reasonable emery that you were thinking about?
So a canonical emery has mass ratio 10 to the minus 5. That's kind of the most typical scenario we consider. But I'll be showing examples where epsilon is actually equal to 1. So it's a parameter you can set to be anything. For an emery, it's usually 10 to the minus 4 down to 10 to the minus 7, typically. That's what we expect to observe. So it's quite small. Now, we don't just use this to describe the motion. like I said, in the setup, the waveform is really tracking the motion of the secondary. And so we actually use this directly in the Einstein equations. We reformulate the Einstein equations in terms of these orbital variables. And then the waveform that comes out from solving the Einstein equations has a very nice, simple structure. So you have a Fourier series in these phases. So this is for an individual spherical harmonic mode of the waveform. And you have this nice discrete Fourier series in each of these phases of the motion of the secondary. And then you have these amplitudes in the Fourier series, and each of these amplitudes is slowly evolving with the evolution of this parameter, or these set of parameters. And now the way we organize our calculations and the way we set goals and what we're trying to achieve is we look at what contributes to these different terms. So this leading term we call adiabatic order, and it's determined by the dissipative modes of the first order metric perturbation. So the modes that are carrying off energy and angular momentum, for example. Then the first subleading term we call first post-adiabatic order, or 1PA. And this is determined by dissipative modes of the second order metric perturbation, and then also all of the first order one. So another way to say this is you need the dissipative first order cell force for 0PA, you need the dissipative second order cell force for 1PA, and you need all of the rest of the cell force for 1PA. And this has really been the long-term goal. It wasn't formulated quite like this, but this has been the long-term goal over the past 20 years to achieve first post-adiabatic accuracy for Emery waveforms. Actually, maybe I'll say a bit more about the reason for that. So the reason for that is that the phase accumulates a lot over an inspiral. It accumulates, say, 10 to the 5 cycles. And the evolution of that leading phase is coming from this 0PA term. The correction is contributing an amount of cycles that is independent of the mass ratio. So it would typically be about 10 cycles, perhaps. And then the next term after that is small with the mass ratio. Its impact on the final phase is small in the mass ratio. So we'll go to 0 with the mass ratio. And we know that for Emery's, if we go to 1PA, we have very precise parameter estimation. If we stop at 0PA, basically we're less accurate than we expect LISA to be.
Can I comment on this transparency? So the two sets, the previous transparency, please. The two sets of equations, I think, are describing there is a difference or a different standing for both. One of them is an expansion of the equations, that's the first set, and the second one is an expansion of the solution. I suppose for simplicity, an intermediate step is missing, which is the equation for the waveform in terms of its sources.
So I'm
So these
skipping.
are two quite different things. It might be easier, for instance, to find corrections to the equations, and then you want to find solutions to the motion as well.
So it's not quite like that. So I'm skipping the expansion of the Einstein equation, which is where you get your waveform from. But as I said, we formulate the Einstein equation directly on the orbital phase space. So we kind of throw away space-time and we formulate the Einstein equation on this product manifold of phase space and space. So I didn't want to get into those technical details, but the idea here is all of the functions are being expanded at fixed phase space variables. So the whole metric, not just the waveform, the whole metric is being expanded in that way. And these forcing functions are being expanded in that way. So when you say expanding the solution, that's a bit different than what's happening here. So that would be more like if you expanded everything here at fixed time t, in powers of the mass ratio. And you can do that, but the waveform you get out is massively less accurate. Okay, I'm already running low on time, so let me try to zip through the rest.
Okay.
Okay. So a big advantage of this framework is that it allows us to generate waveforms rapidly, as I mentioned. And the reason it allows that is it splits up the waveform generation into an offline step and an online step. So the offline step can be very slow, millions of CPU hours, for example. And then the online step is very, very fast. So in the offline step, we solve the Einstein equations for the waveform amplitudes and for the inputs for these forcing functions. So we pre-compute everything on the right-hand side here as functions of orbital parameters, and we pre-compute all these as functions of orbital parameters. That's very slow and expensive, but that's all pre-computed. It's all done in advance. Then the actual waveform generation, all you need to do is solve those very simple ODEs in time for the phases and for the evolving parameters. And then you just add up the mode amplitudes, and there's your waveform as a function of time. And so that can be done very, very quickly. Even if you do a fairly naive implementation, such as this package Wasabi that I've been involved in, you can generate waveforms in seconds. It's in Mathematica, actually. So this is even a very naive implementation is quite fast. Then there's really fast, blazingly fast software package called fast Emery waveforms. And this is where you use GPUs to get down to tens of milliseconds. Okay, so the state of the art in this whole approach, in parameter space coverage, like in what kind of systems we can model, this is at 0 PA, so leading order in this whole approximation. For this, we have a fast Emery waveforms model in the package that can generate Lisa length waveforms for complex orbits quite rapidly, covering a huge chunk of the parameter space. And this is what's currently used in Lisa pipeline development. This is what's actively being used. So here's an example of a waveform generated by Christian Chapman Bird, who over the past couple of years has really been the lead developer of the fast Emery waveforms package. But I'll also give a shout out to my postdoc, Zach Nasapak, who generated all the data that went into this model. Okay, so for the rest of the talk, I'll focus in on the simpler case, quasi-circular inspiral, and ultimately merger and ringdown. So the reason I'll focus in on this is where we have the most accurate waveforms. So at lower accuracy, we can cover a lot of the parameter space. At 1 PA, first order adiabatic, first post-adiabatic order, we covered basically only this, quasi-circular inspirals. And this is work I've been doing with my collaborators Barry Wardell and Niels Warburton for a long, long time, since about 2011. And this is kind of the state of the art of what we've got. So this is quasi-circular with a generic secondary spin. So the smaller object can have a spin in any direction with any magnitude, as long as it's not crazy high, like exceeding the Kerr limit of how rapidly a black hole can spin. But then we were restricting the spin on the primary black hole to be very small. So we're doing a linear approximation in the primary spin. Now here's what you get when you compare against numerical relativity. So as I said, the motivation for developing all of this came from Emery's. But now once you've got the models, you want to compare against existing waveforms. And the best things you can compare against are numerical relativity. But those are only available for comparable mass ratios. So here we're picking the most extreme case. This is equal mass. In blue is the numerical relativity simulation. This is an SXS simulation. This is for non-spinning primary, non-spinning secondary, so a special case. And in orange is our 1 PA model. And here you see, even for equal mass, the model is quite good, especially at relatively early times. It does dephase at the end, and the dephasing here is significant enough that you wouldn't want to be using this for data analysis. But this is the most extreme case where our model will be least accurate. And we know how our error scales. It scales linearly with a small mass ratio. So we cannot extrapolate to how accurate it will be for other systems. But we can also just keep comparing against numerical relativity where those simulations exist. So this is mass ratio 1 to 8. This is with a small spin on the primary, because that's what we are restricted to with this model, but a rapid spin on the secondary. And here you see, because of the higher mass ratio here, or the more extreme mass ratio, our accuracy is significantly better in this case, and we maintain quite good phase accuracy until very near merger. Now you can also take a step beyond this. So doing these 1 PA calculations is really extremely difficult and expensive. And so we're slowly working our way up to doing a full generic spin on the primary, which involves solving all the field equations through second order and perturbation theory on a Kerr background. We're working towards that. But in the meantime, we can try to do the best we can using other available inputs. So because of this very modular construction where we've just got these forcing terms that I was calling F0 and F1 and these amplitudes H1 and H2, etc., we can just put in other information from other models. So for example, from post-Newtonian theory. And we can build a pretty good hybrid. So this is a case where we're using all available exact 0 PA numerical data, all available 1 PA data, because there is a lot of it, just not everything we need for a full 1 PA model. So in particular, all the first order conservative data is available. This is still quasi-circular, but now we're allowing the spin on the primary to be whatever it wants to be. And then the missing 1 PA information we are taking from 4PN. And then we're also adding all the available higher order PN information as well.
Can I ask about the previous slide? Why did you stop it where you stopped it?
I will get back to that.
Okay.
Yeah, that'll be the next theme. Okay, so for this model, this is equal mass and spin of 0.9. And here we see the model is very good. So over most mass ratios, this model is comparable to the state-of-the-art EOB models. For equal mass, I think it's very slightly worse than EOB models, but you can see it's still quite good. And this is really just a very simple model. We have not done anything fancy. We just take all the available information, put it into the waveform construction, and everything works beautifully. Now here in the inset, in the late inspiral, we are comparing against a 0 PA model, which you can see is just total trash. It's terrible. And we are comparing against a PN model, a pure PN with no self-force inputs. And there you see, for equal mass, as is well known, PN actually does pretty well on its own without supplementing it at all, although it is quite out of phase at the end, but you can see it maintains phase for quite a long time. So you might think this model is working quite well just because of the PN input, but the model actually gets even better at higher mass ratios. So this is mass ratio 15, and with a spin of 0.5 on the primary black hole. And here you see we are really extremely accurate. Here we start outperforming the best available other models. But everything we're doing here is restricted to before the merger. And most of the hard effort in those other models is really put into the merger because that's the hardest part for them. So it's a bit of unfair comparison to say that we are as good as these other models when we are missing the most challenging part of the signal. So that leads into the end, which is the merger. Okay, so I've emphasized the structure of this multi-scale expansion, and a key assumption in that whole construction is that the rates of change of those orbital parameters was order epsilon. So I was saying, in replying to Barak, I was saying that we're expanding all of the functions at fixed phase space coordinates, and the assumption is that we can safely expand them all in integer powers of the mass ratio. And that assumption fails towards the end of the inspiral. But we can change how we do things, still using the same basic construction, the same philosophy, but we just change the powers that are involved and the variables we use. So for the inspiral, for a quasi-circular inspiral, you actually just have one phase, not three. You have just the azimuthal phase. And you just have one orbital parameter, which you can just take to be the orbital frequency itself. And so in the expansions I showed before, if you restrict a quasi-circular case, you're just using phi p. We call it p because we're treating the secondary as a particle. So the azimuthal phase and its frequency, those are the two ODEs that need to be solved. Now, what happens as you approach the innermost stable circular orbit is that the rates of change start changing. They're different. In particular, the evolution gets faster as you get towards the innermost stable circular orbit. And the basic phenomenology there has been understood for 25 years from work by Orion Thorne and actually even earlier by Bonanno and Damore. The basic behavior as you approach the innermost stable circular orbit is well known. And what we are doing here is we are extending it to higher orders with this whole phase space multi-scale construction. So rather than using the orbital frequency, we use a scaled orbital frequency, which kind of zooms in on the innermost stable circular orbit. And rather than integer powers of the small mass ratio, we now get powers of epsilon to the 1/5. But otherwise, the construction is actually exactly the same. It's just different powers and a slightly different orbital parameter. Now, this is just to get across the innermost stable circular orbit. Once you're across, then the particle plunges quickly into the black hole. And then that's where the merger happens, in this final plunge. But you can actually keep using this exact same framework, just with different powers of the mass ratio, even in the final plunge. So what you do is, for the final plunge, you go back to just the frequency itself rather than that scaled frequency. And so the frequency here is just the rate of change of the orbital phase. That's how we're just defining it. And we're now back to integer powers of the mass ratio. But what's different relative to the inspiral is that you don't start at or epsilon, you start at epsilon to the 0. And that's because even the geodesic motion here is plunging. So the geodesic motion already has a evolving frequency. And then we can look at corrections to this. And similarly, we decompose our waveform in exactly the same way we did for the inspiral. We just have evolving amplitudes that are functions of the frequency, and then these Fourier phase factors. And so the whole construction works the same. Yeah.
Why not use like a Laplace transform instead of a Fourier to describe, because it's conservative, right, in the plunge. So you could describe plunge.
So the 0th order motion is conservative, yeah. But we're capturing distributive things in everything else here.
Yeah, what I'm saying is that couldn't you bring it to a form where if you use the right variables, the deviation in omega is going to be, order epsilon in these new variables? Like, is the artifact that you have a order epsilon to the 0 and the d omega to the t just a matter of your parameterization?
So yeah, you could use, for example, energy and angular momentum, and then yeah, you'd have 0 rate of change.
Yeah.
So the reason I'm writing things like this is I want to set up basically one continuous waveform model generation where I'm using basically the same variables for every phase, and the waveform construction is the same for every phase. And then you join together the different regimes at the level of these forcing functions and at the level of these amplitudes. So that's what's motivating this particular approach. But yeah, you could use E and L, and then you'd have 0 leading order rate of change.
And epsilon is the same, has the same magnitude as before.
So as I said, epsilon is a parameter varying between 0 and 1. You can set it to any value. The examples I was just showing were epsilons of 1 or 1/8 or 1/15. I'll show an example in a second.
And
Okay,
in this
so
case, why is it that you need, I mean, it seems that you have high powers of epsilon. So why is it that you need them if epsilon is small?
Well, we want high accuracy. So you'll see in a second that with a leading order result, because it's leading order, whereas our inspiral is going beyond leading order, our merger ring down is not as accurate as our inspiral.
Can you define high accuracy? What is it? What is the accuracy goal here?
You don't know until you have a signal, so it depends on the SNR of the signal. It depends on how much of that SNR is concentrated in the merger and ring down, so it depends how heavy the whole system is. It depends on the detectors. You don't know really in advance.
What is the accuracy goal that you are aiming for?
Better than we've got. So, okay, so let me just make one comment here. Often when I present this formulation, people will say, but how can you get the ring down from the plunge? Because the ring down happens after the particle has passed through the horizon. But of course, as we know from our introductory GR, as far as an observer sees at infinity, the particle never passes through the horizon. So this is an example of the kind of slicing we are using. And the idea is each of these orbital parameters we're defining to be constant along a given slice. So this is just one particular choice of slicing. And the idea is you can keep tracking the particle all the way to future infinity. At every point in the waveform, you have an associated point on the particle. So you can generate the entire inspiral-merger-ringdown entirely parameterized just by the particle motion. This thing I'm highlighting here is the light ring. So this is 3m when the particle's passing through the orbit that the photons can be on. Okay, so here's an example of mass ratio 1 to 10. And this is an inspiral-merger-ringdown model built the way I just described. So this is a 1 PA inspiral. This is a second post-leading transition to plunge, so transition across the innermost stable circular orbit, and then just a leading order plunge signal, merger ring down signal. And I actually should have made a better plot to answer the last question. So here you see that we are quite out of phase with numerical relativity. So numerical relativity is in black. We are quite out of phase. But in fact, that's mostly coming from the fact that we are entering the plunge already slightly out of phase. And our biggest source of error is actually from this transition across the ISCO. But if you look at mass ratio, say 1 to 5, we are still not accurate enough, even just in the merger ring down by itself, for loud signals that we already see today. So our goal would ultimately be to go to next order, actually to go to much higher order in the transition in blue here, but then at least to first subleading order in the merger and ring down. Okay, but once we've got these waveforms, we can actually start exploring interesting physics. So this is our waveform. This is not numerical relativity. And there's been a lot of debate over the past 10 years about how close to the peak does a ring down approximation actually work? So just a sum of exact quasi-normal modes of the ringing black hole. How close to the peak of the amplitude can you get with that kind of approximation? So the peak here, this is only plotting the real part. So the peak of the modulus is somewhere right around here. And with this approach, we don't need to fit this waveform to see the Q&Ms. We can actually just directly, analytically, exactly calculate them. And this work had been done in the past using a similar method for leading order waveform. So this is not new to us. But we were particularly interested in, actually, I think about people in this audience did this first, 2009-ish. So what we are particularly interested in here is how close to the peak can we get? Because there have been claims fairly recently that you can get extremely close to the peak just with a linear superposition of quasi-normal modes. And here we are calculating the exact amplitudes of the exact quasi-normal modes of this waveform and just adding them up. And so here's the leading order, the fundamental mode. Here's the first subleading order. We keep adding, and you see it does keep getting better, but it's always wildly off here. And no matter how high you go, it doesn't get any better at early times. It's always becomes wildly wrong well before you approach the peak. Okay, and I don't show here, but we also did another study of a stationary phase approximation, which actually surprisingly gets us quite close to the peak coming from the other side. And that's also a very simple analytical approximation. But currently, there is a gap in between where you can't model the system either with a simple stationary phase or with a simple sum of Q and Ms. You need to really get the full signal going through the merger phase. Now, another thing we can do once we have these linear Q and Ms, these linear quasi-normal modes, is we can start to investigate nonlinear effects. So this is kind of a step towards a complete subleading order merger ringdown signal, but focusing on late times when the ringdown approximation is accurate. So this has been a big area of excitement over the past maybe 4-ish years, maybe, of nonlinear effects in the ringdown. So at linear order, your ringdown is just a simple sum of exponentially damped sinusoids, basically, with complex frequencies. So it's oscillating with a distinct frequency and it's damped with a distinct decay rate. At second order, and if you look at the second order Einstein equations, we have products of things like this. Well, you generate new modes that are simple sums of these first order modes, of these linear modes. So you have what are called quadratic QNMs or QQNMs, which is a simple sum of first order ones. And what got people really excited about this is that people could actually see in numerical relativity simulations signatures of these QQNMs. And then this becomes, a unique signature you can look for in real data. You can look for these nonlinear effects in real data. You can potentially this will have a big impact on, say, black hole spectroscopy in real data. So where you're looking for specific frequencies and seeing how well they match the general relativity prediction for a black hole. Okay, so we can do that with our waveform. We can take our first order QNMs that we know exactly. We can then solve the second order equation just at late times using the QNMs as the first order QNMs as input to the second order field equation. And then we can look at the full signal that involves linear and QNM. And what we see here is that we do have the linear piece dominating. So this is the fundamental mode from the linear waveform in blue. This is on a log scale, so things that are exponentially damped look basically like straight lines. And then you have linear effects that are subdominant. So this is the first overtone, the second overtone. But actually the quadratic effect, the QQNM effect, is dominating over the higher overtones. And we find this is very consistent across the board for any combinations. The QQNM is typically bigger than the overtones. And this is important because when people were fitting numerical relativity data, for a long time, this is no longer so much the case, but for a long time, they were really just using lots and lots of overtones, lots of linear approximation, which is just actually a bad approximation. The quadratic effects are significant. Another quadratic effect we can look at, I do realize I'm over time, so I'll skip the whole last bit. Another quadratic effect we can look at when we use our first order signal to then generate quadratic effects is the nonlinear memory through the merger. So up top, we're looking at numerical relativity, and on the left is a signal with no memory in it. And for those who don't know, memory is like a long-term shift in the waveform or in the displacement of test masses. On the right is the full signal, including memory, and what you see here is through the merger, the entire signal shifts up, And this corresponds to a permanent displacement of test masses after the signal has passed through those test masses. Down here is what we get with our linear signal inputted into a second order calculation, and it looks the same as NR. And in fact, you can calculate it right around the middle here, and it looks exactly like NR, like really close. Okay, so I will skip this last few bits, which I expected I would have to, and just wrap up here. Okay, so self-force theory, it was designed for emeries. It was always known it would be good for emeries. It's now known to be highly accurate for what are called intermediate mass ratio inspirals. So systems with mass ratio 1 to 100, 1 to 1,000. And we're finding it works really quite well for mass ratios more like 1 to 50, 1 to 20, 1 to 10. And with these kinds of things, we expect to be able to do high precision tests of general relativity, probes of environments and galactic cores, all these things with emeries. But there's other advantages to self-force, not just associated with emeries. So we have very fast waveform generation. We have this really unique inroad to doing merger-ringdown calculations that was not available without self-force. Because of the modular construction, we can readily include beyond GR effects. And the slides I skipped were showing how we can do that in the merger and ringdown. And another advantage is we get kind of a semi-analytical description of the entire binary evolution, inspiral-merger-ringdown, that then allows us to really explore specific effects in fine detail that's very difficult to do with numerical relativity, for example. Okay, I realize I'm way over time now. Sorry for that, but thanks for listening.
Thanks, Adam, for a great talk. Any questions?
So I just wanted to make one comment that perhaps the reason you're doing so well for comparable mass ratio is that the small parameter is really the mass ratio times some power of velocity, just because the radiation is suppressed by orders of velocity. So even if you don't have the mass ratio there, you still have something like v to the fifth. This is also why you get kind of close, but in the end, it kind of gets ruined.
So at early times that is true that the rate of change of parameters is like a universal small parameter in the inspiral. It's small in PN, it's small in self-force, and if you combine it, it's really small. So everything's working in your favor. Another thing to realize is that we actually should not be surprised at all by this level of accuracy. It's really what you would expect just from naive estimates. So one thing I didn't mention is that in all these models, once we have our final evolution equations, we no longer use the ordinary mass ratio as our expansion parameter. We re-expand everything in the symmetric mass ratio.
Mm-hmm.
And the symmetric mass ratio is equal to a quarter for equal mass.
Mm-hmm.
So our subleading things, even for equal mass, are mildly suppressed by that quarter.
Right.
And if you look at the accuracy of our waveforms, it's actually totally consistent with what you'd expect just from that scaling.
I see. Okay.
So for Q equals 1, like you could even say, wait, this is bad. We should have a quarter radian dephasing.
I see.
Whereas instead here we probably have around 1 radian dephasing.
I see.
So yeah, it's not actually unexpected. It's just that you could have been deeply disappointed by having massive coefficients in these expansions.
Right.
And then you would find very poor accuracy.
Right. Makes sense.
But yeah, your point is very good that for the inspiral, there's multiple things working in our favor.
More questions?
I have one more just just if nobody's asking. What's the latest on the in the second order self force on the infinite coupling problem?
Yeah, so what we do now, were you at Capra? I don't remember. Yeah, you were, right?
Yeah.
Yeah, so what we do now, what we're aiming towards is what we were showing at Capra, which is to not take advantage of the separability of the field equations, or
Mhm.
take less advantage of it, and to not decompose into spherical harmonics. And that has led to massive gains in our speed, because the problem Ofri is referring to is that if you expand everything in spherical harmonics, then you go to second order, you have coupling between all these different harmonics, and you end up needing basically infinitely many of them near the particle. And so what we're doing now largely avoids that just by avoiding the expansion in spherical harmonics, and that has led to a speed up of about 100,000. But we still don't have the second order Kerr calculations working.
Right. Right.
Any day now, any day now.
Interesting. Okay.
So a question about Lisa. So you were saying that you can get the spin to 5 or 6 digits of
Yeah.
accuracy. So how many quasi-normal modes will we be able to actually
Ah,
measure?
so unfortunately, these are two different regimes. So with MREs, we will get
Is
very
that
precise. Yeah, so for MREs, we'll get very precise measurements of the primary black hole parameters, but we'll get nothing about quasi-normal modes. Except there is a case where if you have very, very eccentric orbits, then the secondary can get very close to the big black hole and it can then excite quasi-normal modes. So there's the potential of seeing those, but it's very unlikely that we'd see more than the fundamental mode. For the actual merger and ring down, for MREs, it contributes so little to the signal that we won't get anything really.
Mm.
But for uh, one potentially interesting case that I don't know if people have done real parameter estimation estimates for would be if you have massive black hole binaries. So massive black hole binaries where we have two massive black holes, they can actually have, or they're predicted that they will actually, that there will be some number of them that has a very high mass ratio. So not Emery regime, but like mass ratio 1 to 50, 1 to 100. And that's a case where our models should be quite good. And for those, there could be the prospect of really seeing the merger and really seeing QNMs. But by far the best prospect for QNMs is just massive black hole mergers with comparable mass, um, in which case the signals, this method will not be accurate enough because the SNR is so high for those systems.
But these events presumably will be pretty rare, no?
The high mass ratio ones
Comparable.
or comparable. So for massive, yeah, okay. So the event rate estimates for massive black hole binaries are probably even less definite than for MREs. So you see estimates of anywhere between less than one per year to maybe tens per year, which could mean we don't see any of these massive black hole mergers, or it could mean we're just totally swamped by them and they overwhelm everything.
Okay, so it's very uncertain.
Yeah,
Okay.
yeah. I think the
Shahar,
peak.
what is certain is that at least initially, they will focus on the extremely high SNR uh, events, which if presumably some of them do exist, and then these will be the mergers that Adam was talking about, and the rest would be really swamped by this noise and all of that. And I think you didn't mention the fact that if we do get lots of memories, then there's a big problem in terms of data analysis,
Yeah,
separating them and so on. So,
yeah, yeah,
so most likely, if Lisa flies, then the first signal would just be from what we expect, massive black holes merging, and that's it.
That depends on the event rate. Definitely, what we will absolutely see is a foreground of white dwarf binaries. We're going to see tens of thousands or hundreds of thousands of individually resolvable white dwarf binaries, and a lot of the effort on doing the global fit. So data analysis for LISA is going to be totally different than data analysis for LIGO. Because all these signals overlap, you need to look for them all simultaneously. And a lot of the work on global fit so far has really focused actually on the white dwarf binaries because we know they're there and we know there's a lot of them that we're going to see as soon as we turn on the detector. And then massive black hole binaries as well as kind of the next thing you look at. Emery's right now, the global fit analyses have not looked so much at Emery's, not because we don't expect to see a lot of them, but because right now we're not even sure how to find individual Emery's as part of the global fit. So there needs to be a lot of work, really actually over the next 3 to 6 months in making sure we can find Emery's. That'll be a huge focus of what's currently happening in the DDPC, which is basically the data analysis center that will be analyzing all the data.
One more question. Have you tried to see whether your method can be applied to ET data or Cosmic Explorer data? Because we expect a Q of 50 would probably happen sometime.
That is an excellent question.
Thank you.
So yeah, this was really what we were hoping for once we had the merger and ring down in our model to start looking at forecasts for Einstein Telescope and Cosmic Explorer, as well as looking at currently detectable signals. The reason we have not yet done that, okay, there's no good reason. We will do that, yeah.
I was surprised to see how sensitive, how this factor of 10 in sensitivity affects all these kind of detection possibilities. And
Mm.
it seems that if your method works for Qs that are of order of tens, then it's actually quite interesting. I have a personal interest in memory, so
Yeah, I think that'll be really exciting. And I don't know what the latest estimates are for uh, length of signals we'll see for IMRIs with 3G detectors. They used to be very optimistic that we would see really long signals for mass ratio 1 to 100
so
with
the last I heard, but there should, at least for me, there should be, maybe Ofek knows more, but there should be a new version of an estimate for event rate. The last that I heard was very disappointing. It was they couldn't even make a good estimate for the one event of Q of 30 that was observed in LIGO.
Okay, that is disappointing.
But I'm sure that it doesn't feel right. It seems that they should see at least a few of 50.
Yeah, they should see a lot. But I think another bad thing that's happened is that the old estimates were um, were based on a low frequency floor of 1 hertz. And now most people working on these things say, no, we're never going to get that low. It's not going to be anywhere close to 1 hertz, which really cuts off the length of the signal that you can see uh, with these IMRIs.
Okay, great. So, any final quick question? So if not, let's thank Adam again.
Thanks.
Well, thank you for letting me run way over time.
I'll stop.